In this session, we'll discuss about the working. The same figure is there again. The pink ones are adjustable wicket gates or guide vanes. In this picture, this outer ring is having these vanes, that is these vanes. These vanes are adjustable guide vanes. The inner part is a runner. So there is entry point, the water enters at this point, water leaves the runner at this point and it goes down. So we'll see these comments. General feature of Francis turbine. So what we have is a speed ratio definition, or it is also called a speed factor in reaction turbine, represented by phi. In impulse turbines we used to represent this as Ku. Similar thing is this speed ratio, that is velocity of vanes divided by root 2 gh, and this u can also be given by pi dn by 60. The diameter is different because here at the entry the diameter is bigger, and then at the exit when the water comes out of the runner the diameter is less. So d1 is the entry and d2 would be exit diameter. So d1 diameter at inlet, and n is the speed in rpm. So for Francis turbine, this speed ratio or speed factor is taken 0.7 to 0.85. If you remember, in impulse turbine we used to take Ku as 0.43 to 0.47. So here it is much larger. Now there is as speed ratio, there is one more definition, flow ratio, represented by psi, and this is the ratio of velocity of flow to root 2 gh. So root 2 gh is there in both the cases in the denominator. So if it is a speed ratio, it is speed of blade of runner. If it is a flow ratio, it is speed of velocity of flow. So now the most important thing, generally velocity of whirl or swirl velocity, you know that velocity of whirl VW at outlet is kept zero in Francis turbine or in reaction turbine in general. So VW2 at outlet is VW2 is kept zero. The meaning is the radially outflow is the general design feature. So if you look at this outlet velocity triangle, in line with this we have got relative velocity, then we add velocity of vane to get absolute velocity of the jet. This jet is now making an angle of beta. The components of this absolute velocity in the direction of u is known as VW2, and this is made zero in the sense this V2 comes out radially, or VW2 is made zero. That is what is the general feature of the reaction turbines. Now if you recall the T, the torque, I'll go slightly further and show you. So this slide we have already seen when we discussed series of vanes on radial float of impact of jets. So this particular formula where momentum etc. is considered, so output or work done is given by rho A V1 rho Q, so that is mass rate of flow, and this is VW1 U1 plus or minus VW2 U2. In this VW2 is becoming zero, that's what we are trying to tell. We'll go back to that slide. So here, so torque is given by rho into Q, mass rate of flow, VW1 R1, this is torque, minus plus or minus, of course, VW2 R2. If beta becomes more than 90 degrees, it is minus. So power is equal to T into omega. Then when omega gets multiplied with R, it becomes U. So this is what we are looking at. Work done per unit time is power. It is rho Q in the bracket VW1 plus or minus VW2 U2. But if we make VW2 0 as per the design case, then simply it becomes rho Q VW1 U1. Now hydraulic efficiency is defined as power at the shaft divided by gamma QH. Now power at the shaft, now it is becoming VW1 U1 plus or minus VW2 U2 divided by GH. This is gamma QH. Because of that, these terms get cancelled. You will be left with this. And then once again, if VW2 becomes 0, the hydraulic efficiency equation becomes only this much, that is VW1 U1 divided by GH. And these velocity triangles already we have seen. This is inlet velocity triangle with the same notation. Alpha angle made by the jet, theta angle of vane at the inlet, then this horizontal distance whole thing is VW1, and this particular component is velocity of flow VF1. Outlet velocity triangle, you know that V2 absolute velocity of the jet, this component in the direction of U is VW2 and this is VF2. This is velocity of flow. This we have already seen. Same thing is there here. This I'll explain in next video.